Alright, in the last few tutorials we saw how to manipulate a structure with VMD, especially save certain chains inside the structure and save a fragment of the structure. And then we followed that up with modifying a particular fragment, especially fragments of the ligand, to delete parts of the structure and also change the stereoisomeric form from L-Asp to D-Asp. And then finally we modified the residue names and the chain IDs using PyMol. So we have a ready-made structure of the complex here, which is L-Asp bound to AspRS. So in this tutorial, we are going to use that structure as a reference structure of the complex to model the interaction of the ligand with that of the receptor, that is interaction of L-Asp with AspRS. We are going to achieve that by using a method called docking. So first, we will need to separate the structures of the ligand and the receptor into two different PDB files, then do a constraint-based docking of the ligand into the receptor. So we'll use two different programs. First is AutoDock Vina to carry out the docking process, and secondly, we'll use UCSF Chimera software in order to access the AutoDock Vina from here. So AutoDock Vina is integrated with the UCSF Chimera, but you need to install both of these softwares separately. So before we begin, I just want you to have a look at the right panel here as once you open the Chimera. So you'll find the history of the structures that you've opened before. So you can access any of these PDB structures. So firstly, we'll go through the traditional process of opening the file, although I can access the file from here itself because I have opened this file before, LASP AspRS mod. But I'm going to go to File and then click Open here, and I'm already in the working directory, which is Workspace 1, and this structure is highlighted here. So I'm going to go ahead and open it. And as I've told you before in the previous tutorial with Chimera, that you can change the background if you want. Personally, I prefer a white background because I feel that it's of a much greater contrast and the different molecular components are visible clearly. You're most welcome to use the black background as well if you want, if that suits you. So we are going to go ahead and set the preset for a white background, which is a pre-saved template that the Chimera program has. That's publication 1. So you see it's a much clearer contrast now with the white background. So another interesting feature of Chimera is the display of the binding site residues as soon as you open the structure. So if there is a ligand present in the structure, it will show the binding site residues in the receptor that are involved. The reason being, since the ligand is not part of the receptor or is not covalently bound to the receptor, therefore Chimera is automatically able to recognize it as a non-covalent interaction with the receptor, and that's why it shows the binding site residues. Here you can see these residues displayed in licorice. So all the important residues are displayed here. Okay, so we will begin by separating the structure of the receptor from the ligand and writing one PDB file each for the ligand and the receptor. That's L-Asp and AspRS. So as I've showed you before, we can achieve that by selecting specific residues here. So if you do select and go to residues, then you find all the residues being listed out here. But then again, as opposed to the last time when we operated on Chimera, we found that the residue name for the ligand was AMO and it was displayed here on top. But since we have changed the residue name of the ligand to a standard residue now, that's L-Asp, so it has this 3-letter code ASP, so it's merged with the receptor. And if you go ahead and select this from here, will actually highlight all the aspartic acid residues that are present in the complex. So that's pretty undesirable and inconvenient. So another workaround, and you might remember that we changed the chain ID of the ligand from A to B. So a workaround in that respect would be to select the chain ID, the respective chain ID. So now you know why we did that operation. So we go to select again and then select by chain. So you know that chain A is the receptor itself. As you can see, the receptor is highlighted completely while the ligand is not. And then chain B is the ligand itself, which is the L-aspartic acid. So you see now the ligand is highlighted properly. We'll first go ahead and delete the structure of the ligand to create a new structure for the receptor only, because the ligand is already highlighted here, so it's easier for us to delete the ligand first. So we go to Actions, Atoms or Bonds, press delete. There you go. The ligand structure is gone now, and now we have only the structure for the receptor, which we are going to save as a separate PDB file. So you go to File, Save PDB, and then name it as receptor.pdb. So we are already in this directory, the workspace one. And we'll use untransformed coordinates again. So we save this here, and next we are going to save the structure of the ligand. But as you know that the structure of the ligand is already gone from here. So what we'll do is we'll close this first and open Chimera back again. So you have applications and then Chimera, you can load it from your Windows desktop. So you see already the structures are listed out here. So the receptor structure that we saved previously is also listed alongside the structure of the complex that we opened initially. So we are going to click from here directly and open the structure for the complex, and you see the ligand is intact now. So just go to presets and change to the publication view with the white background. So now we'll delete the structure of the receptor and retain the structure of the ligand only. So go to select again, select the chain A, that's for the receptor. Go to actions, atoms or bonds, delete. Boom, the structure for the receptor is gone now. You only have the structure of the ligand, that's L-Asp. I want to save the structure of the ligand now as a separate PDB, but before doing that, we would like to transform or translate and rotate the molecule a bit so that it's further away from the binding pocket. The reason why we are doing this is because you don't want the positions, the 3D coordinates for the ligand to overlap with the already available experimental structure of the complex that we have, so that we can use the structure of the ligand as a starting structure for docking with that of the receptor. However, we do not transform the coordinates of the receptor because we want it to be as it is, and we want the ligand to be away from the receptor so that when it's actually being docked, you can see that it's the result of the docking, and it will give you a better comparison with the experimental structure. So let's go ahead and save this. Zoom in a bit more. Yeah, just play around with it, and once you're happy, just go ahead and save it as a separate PDB. So save PDB. And here's the thing. So previously you might have seen we used untransformed coordinates for all the other structures that we have saved, because no matter how much you rotate or translate, the coordinates of the structure remain the same. But in this case, if we uncheck this option, then whatever translation or rotation that we have done on the structure of the ligand will be saved, and the coordinates will change as well. So that's what we want, right? So I already have the file name here as ligand.pdb. So I'm going to go ahead and save it. There you go. So the structure of the ligand is saved as a separate PDB. So I'll have to close this again and then further open up Chimera once again. So as you can see, the structures are listed here. So first, let's go ahead and open the structure for the receptor that we saved previously. So that's this one. Just change the preset to publication 1 here. And then we'll go ahead and open the structure for the ligand, which is ligand.pdb. Open. So you see it's slightly transformed from the binding pocket, not that much, although I would have desired that it would get transformed or translated to a much greater extent, but it's not actually. So that's fine, but still it's not actually holding on to the binding pocket residue, which you can confirm by the fact that the binding pocket residues are not showing up here. All right, so now the important thing to note here is previously whenever we were loading the structure for the complex together with the ligand and the receptor, it was loading as a single model. That's model number 0, let's say the first model that's annotated by UCSF Chimera. But once we have both the structures for the ligand and the receptor open separately, they will be annotated separately as 2 different models. So model 0 stands for the receptor because we open that up first, and model 1 will now stand for the ligand here. So if you hover over these residues, you'll find #0 for the receptor, any residue on the receptor, and #1 for any atom on the ligand. itself. You can access these two models by going to Favorites panel and then opening up the model panel. So once you open up the model panel, you will see ID 0 is annotated for the receptor and ID 1 is annotated for the ligand. So that's pretty handy because we can then operate on a model basis for the constraint docking that we are going to perform. All right, so let's get started with the actual docking procedure. So we can fire up AutoDock or open AutoDock by going to Tools menu, and then we'll go to Surface of Binding Analysis, and then you see the option for AutoDock Vina here. So you just click on it. A new window will open which says AutoDock Vina on top, and it will ask you to save an output file. Now, for all the docking procedures, for most of the standard docking procedures with AutoDock or AutoDock Vina, these kind of packages and softwares, you'll have an output file with an extension of PDBQT. So this Q at the end of the extension stands for the charge that will be implemented. So during the docking process, all the atomistic representations or all the atoms are having a particular charge, and that's being assigned by the specific docking method that we'll be using. In this case, it's AutoDock Vina's specific kind of charge that they will be using. That will be assigned in the output file itself. So that'll help to assess the electrostatic interaction between the ligand and the receptor. So let's name it as complex.pdbqt. So you see the extension here is pdbqt. So just to confirm, we're in the same directory where we are running where we have opened the structures from. So yes, we are in workspace 1, and then again we'll type in the name of the complex structure that we want as an output for docking. So it already says here add .pdbqt suffix if none given. So we'll set the output location. So everything that's happening with the docking, the results of the docking will be saved out here. Excuse me. Now we have an option for selecting the receptor and the ligand. So as you can see, model wise, the receptor is already selected here in place of the receptor, and for the ligand we'll change this to model number 1. That's the PDB file for the ligand itself. So if you go further down, there are a number of search options. So the search volume option. So the way this AutoDock Vina operates, or any other docking software for that matter, is basically it creates a box around the binding interface or the region of interest in the receptor that you want to explore. So it is always handy to have a previous idea about the binding site. Otherwise, we'll end up doing a blind docking, which is very undesirable, which means you don't know anything about the binding site residues in a receptor, and you just place the ligand and let it bind anywhere it wants, especially in this case, in case of a receptor which is so big and a ligand which is so small. This is undesirable because the ligand will bind anywhere and everywhere and not actually to the binding site. It may not bind to the binding site at all, because if it finds a more favorable interaction in some other site, then it will go and bind there. But what we want out here is for the ligand to bind to the actual annotated binding site, the known binding site. So it's always useful to have a pre-notion about the binding site. All right, so as I said that we'll need to create a box around the binding pocket. So for that, let's go ahead and redefine the binding pocket first. So if you remember from the previous Chimera tutorials, we can do this by going to the command line from the favorites menu. So once we go to the command line, we'll have an option to type in the command and select the specific residues. We did that previously for a few residues of the binding site, but out here I already have the specific residues of the binding site, as you can see. And so the way it works is basically #0, that's the model number, followed by the residue number, followed by the chain ID. So #0 colon 171.A would be 171st residue in chain A. That's the receptor itself. So The binding site residues that are annotated, I have posted those in the slides as well, and you can refer to them, are 171, 195, 198, 217, 448, 489, so on and so forth. So in order to represent this, let's say in a licorice representation, we are going to click enter here first for them to get highlighted, and as you can see, they are highlighted now. This is also a further confirmation that the ligand is actually away from the binding site. Otherwise, in the original crystal structure, you would have found the ligand somewhere here. Okay, so once these residues are highlighted, we are going to go back to actions again and atoms or bonds, and then show. So this shows up the binding site residues. Now what we are going to do is, actually before that, since we are going to create a box around this, it might as well happen that the ligand might be present inside the box. Like the box might be big enough to accommodate the ligand as well. We don't want that. So we're going to go ahead and first remove the ligand. So we can do that by going to favorites again and going to the model panel. And if we uncheck one of the models, it will not move. I mean, whatever you do with the mouse out here, rotate or translate, if you uncheck one of these models, that particular model will be unmoved, whereas the other model will move. So we don't want the receptor model to move. We only want the ligand model to move. So we'll uncheck this, the column A, below the column A, the box below the column A, and then translate the ligand further. So press on your middle mouse button and just drag along so that it's enough outside the binding pocket. So you can see it's very much outside the binding pocket. You can further rotate it if you want. Now we are going to reselect, we are going to recheck this option for the receptor, because now we want both the receptor and the ligand to move around together, and close this. So we are going to go ahead and create the box now, which is also known as the search volume. Basically a rectangular box containing search spaces in which the ligand can float around and change its conformation and the dihedral angles and different torsional potentials. So it has got certain torsional degrees of freedom which it can explore around, and the phi and psi angles can change around, and it can adapt a specific comfortable position inside the binding pocket. So the search space, the search volume, or the rectangular box is important to be defined, and it should be large enough to accommodate the ligand in a certain search space. However, it should also be small enough in order to just accommodate the binding site residues and not any other residues which are unlikely to bind the ligand. Okay, let's go ahead and define the search space or the rectangular box here. So we'll check this, and it says which button do you want to use in your mouse for defining the rectangular box. So I usually prefer button 3. That's the right click. It's very convenient. And rather than writing out the center and the size out here, we'll just go ahead in the interface itself, in the GUI interface, and then once you right click, you'll find that a box is created here automatically. So first let's change the color of the box to something more suited to the eye. So we go back to the model panel, and as you can see, the color is lime green here, sort of fluorescent color. We can change that to, let's say, a red color. Yeah, it's way better and much more prominent. Okay, so close the model panel again. And now how to resize the box. So the way we do it is right click on the mouse and drag along the edges. So if you right click on your mouse and while holding the right button down, if you drag along the respective edges in the XYZ direction, the box keeps on expanding, and you can compress the box as well. So we are going to fit the box just enough into the binding site. As you can see already that in this direction it's a much bigger size, so we are going to go to this edge and then right click and drag along so that we reach almost the end of the residues here that are defined by the binding site. Okay, so this is a bit of work, but you want to be as precise as possible because that will lead you to a better docking result, an accurate one as well, to compare with the experiments. Almost there. Okay, this side needs to be compressed further. All right, and now we look at it from different perspective. Oh, there you go. So in this direction, it's almost out of the binding pocket. So once, in order to drag the box as a whole, as opposed to one of the sides, you go outside the box and then right click and then drag it along. So the box in itself is dragged along. And then you adjust this edge here slightly. And then go in this direction as well, and this one. Okay. And a bit more here. So you see, precision is very, very important, and you want to be as precise as possible. So I guess we are nearly there, and we should be happy enough with this. So some portion of the box is outside, well, not outside, but it's covering a larger area out here, which we can further compress down like this. Okay. All right, perfect. So we should be fairly happy with it. Okay. So now once we have defined the box here, we'll go to the other options, that is the receptor options, and we would ideally want to keep everything default, but let's go one by one of what they say. So add hydrogens in Chimera, true, okay. If there are some missing hydrogens, you want to add them up. And then merge charges and remove nonpolar hydrogens, all right, we can do that. Merge charges and remove lone pairs, that's fine as well. Ignore waters, because docking procedure does not involve water. So if you obtain the crystal structure as we originally obtained for this protein, Aspartyl-tRNA-synthetase, it had some crystal water molecules in there while it was being solved by X-ray diffraction method. Excuse me. So you want to ignore that as well. So you ignore those explicit waters and then ignore chains of non-standard residues. All right, that's true. So ideally, you would want to include the non-standard residues to participate as well in the docking process. So by non-standard residues, it means any other residues apart from the amino acid residues in the protein. Like, let's say if you have a metal ion or any other non-standard residue that does not belong to the part of the protein. And those might be important for the interaction with the ligand as well. But once it says chains of non-standard residues, which means that the non-standard residues are defined as a separate chain, you don't want them to be included. So the very next option here, which says ignore all non-standard residues, on the other hand, is set to false, which means you need to include the non-standard residues here. All right, let's look at the ligand options that we have here. So under the ligand options, we have merge charges and remove nonpolar hydrogens. We don't do that. And then merge charges and remove lone pairs. We don't do that as well. So we keep these options true for the receptor, but not for the ligand. There's another advanced option setting where you have the number of binding modes. So basically the number of structures that would be ranked hierarchically, the complex structures of the docked ligand to the receptor. So based on their binding affinity or favorable binding energies. So the maximum that you can have with the UCSF Chimera is 10, whereas if you use AutoDock Vina as a standalone package, then you can have many more structures, even hundreds. And sometimes some of the structures in between, like further down in the hierarchy, let's say structure number 50, ranked 50 in the hierarchy, can be important as well because of the binding pose. But most of the time, the first 10 structures are the most important. So the exhaustiveness of search. So the search space that it will use to search the specific poses, the different poses according to the change in conformation and the torsional freedom that the ligand has will be based on certain grid spacing. So the exhaustiveness of the search in the grid space is set to maximum. So you can have levels from 1 to 8, so we'll set it as maximum. And then there is the maximum energy difference, which means how much of an energy difference in kilocalories per mole do you want between the structures of the docked ligands the binding energy differences in order for them to be considered as a separate cluster altogether, like a cluster of docked structure separated from a cluster of another docked structure. And then you have the options from where you want to run the program from. So you can either run it from the web service, that is access the internet from here and run it via the AutoDock web service here, which never worked for me actually. I don't know, for some reason the servers are down always. But you can, once you have the AutoDock Vina installed on your local machine, you can run it locally from here by defining the path. So I have it inside user local bin Vina. You might have it in a different option, a different path altogether, like Windows might have a different path. So you can browse here and select the specific path where your AutoDock Vina binary is installed and locate there, and then click on this and this will automatically select the path for you and it will run it from there. Okay, so once we have all the options and the settings set up, we can go ahead and run the simulation, the docking simulation. So we'll just set it in a way that we can see clearly the binding pocket and where the ligand binds. So we'll just play around with the rotation and get to a certain position where we're happy about, get a better view from the gallery, let's say. Okay, let's stick with it. Okay, that seems decent. So here's the ligand and there's the binding pocket, so we can easily see it go there. All right, now is the time to start the docking simulation. So we have everything ready and we click on apply. Okay, once we click on apply, we can see that the docking process is running. As you can see, the mouse pointer is changing its appearance, it's doing some work, and there you go. That was fast. So as you can see that it didn't need to do an exhaustive search because it found a perfect fit with a limited number of search space, because we already predefined the binding pocket, and the binding pocket resembles a region which is, you know, close enough and a properly defined pocket. Once you have a surface representation of this receptor, you can see it more clearly. If we had not defined the binding pocket, then the search space, the procedure to, you know, locate in the search space a proper binding space would have taken much longer, and it would have been much more exhaustive search. Anyway, so as you can see, the results are displayed on the screen in a new window, which is basically the score, which is defined as the binding affinity. It also defines the energies in kilocalories per mole, but then again we don't consider the energies of the waters here because this is a docking in vacuum basically. So this is mostly the van der Waals energy that it uses, and it estimates, it has an estimation of the electrostatic potential via the hydrogen bonding. So AutoDock Vina doesn't really calculate the electrostatic energies directly. So these are ranked according to their binding affinities. So the lower the score, the better the binding affinity. So negative 5.6 is the score of the first model. And if you highlight the second one, so if you can ignore this part, this is the ligand that was originally present in the position that we used as a starting structure for docking. Now if we can zoom into this, we'll find that actually, you know, we have highlighted the binding site residues. So this is a distraction. We are gonna hide this binding site residues. So actions, atoms or bonds, hide. So once you do that, you can only see the ligand. So you see the ligand is the first most favorable structure for the ligand. Docked ligand is bound to a position which is sort of in the center of the binding pocket, which is fascinating. It's very encouraging, and it's almost also exactly inside the box. Okay, you just deselect this model so that, you know, it doesn't act as a distraction. So that was model 1, so we can just not show it here. All right, so this is the first in the rank of the docked ligand. Let's see the second one. Second one also is in the same position, but it just rotates itself a bit and it changes its configuration a bit. That's it. How about the third one? It's almost in the same position. So all the first 3 models at least are binding to the same position, which means this binding pocket must be very favorable for this ligand. And then you go to the fourth one, the fifth. So in the fifth one, you can see it's moving further slightly away from the binding pocket. That's why it's placed lower in the ranking of energies. Then you go to the sixth, which is again a bit away from the binding pocket. The seventh. So as long as it finds a more space out here within the box, it won't go out of the box at any point, but as long as it finds more space in here, search space, it will just keep on creating new configurations. Whereas 99% time you can be assured that the first model in the hierarchy is the model to go for, is the best fitting model of the ligand with the receptor. And then finally model 10, where it's also a little bit away from the binding pocket. So compare that to model 1 again, you see it's perfect fit. Okay, so we are judging this based on the binding affinities themselves. But how about when we compare them with the experimental structure? So we already saved the experimental structure previously with the L-Asp modified residue. So we modified the AMO to ASP in the ligand. And we can just overlap, so we can just align the structure of that ligand with this one by opening up the structure file for the saved complex. So the name of the saved complex was LASP AspRS _ mod.pdb. So we're going to open this up, and you'll find that the receptors are aligned to each other. Again, the binding site residues are showing, which are distractions, so we are going to remove them first. So you can just select these again. That's for model 0, and now that we have loaded a new structure of the complex, that would be model 2, I guess. Oh no, model 4. So the model 2 stands for the search volume, and the model 3 stands for the complex PDB-QT structure that was shown as a result here. So this new model that we loaded here, L-Asp AspRS mod, is actually model 4. So it's just gonna, we're just gonna change the model number here for the selection from model 0 to model 4. We can just select all of the residues of model 4 such that the licorice representation will be gone, whereas the ribbon representation will still be there. So let's go ahead and just delete this part altogether and just have all.a. So there you go. You have all the selections of, so all the residues in model 4 is highlighted. You might not see them apparently from here, because it might seem that model 0 is highlighted with the ribbon representation, but it's actually an exact overlap of model 0 with model 4. That is, model 0 is the receptor only model, and model 4 is the model of the complex that we newly opened now. So the color difference is not being shown, but rest assured that it's the model 4 residues that we are hiding here, and only the residue for the receptor. Alright, so let's go ahead and actions, atoms or bonds, and height. There you go. All the binding site residues for model 4 are hidden now. So it will give a better comparison with the original experimental ligand structure that we had, and compare it with the very first model of the dock structure that we have for the ligand. So immediately you see there's a significant overlap. It's almost the same. In the red is the newly opened structure, so that's the structure of the experiment that's obtained from the experiment, L-aspartic acid. And in green you have the structure of the ligand that we docked just now, and it's ranked number 1 in hierarchy. So that's great. They are almost overlapping. If we further go down from here to the next structure, we see they are in the same position as well, even with the nitrogen atoms facing in the same direction, if not exactly aligning with each other. Number 3 is slightly away, but not by much. And then number 4 is slightly away as well, and number 5 is a lot away. 6 again goes back to the binding pocket, and then 7 away, and then 8 a little bit away. So yes, number 1 is the way to go to. So we can save these structures directly. Well, you already have a saved file in the complex.pdbqt, and we can extract those structures by doing some post-processing operation. So that's it. Talking with AutoDock Vina using Chimera as an interface. Talking with AutoDock Vina using Chimera as an interface.